Number 50, construct your own problem. On February 14, 2000, the NEAR spacecraft was successfully inserted into orbit around Eros, becoming the first artificial satellite of an asteroid. Construct a problem in which you determine the orbital speed for a satellite near Eros. All right. So here's Eros. All right, it's an asteroid. Here's a satellite that'll be orbiting, right, the asteroid, and the distance between them is about 150 kilometers, we'll say. Also, let's say the mass of Eros is about 7 times 10 to the 15th kilograms. All right, and our job now is to figure out, well, what is the speed of the satellite? The orbital speed, they're talking about the linear speed, aka the tangential speed. So that would be V. We are looking for V. Okay, so remember, we've done plenty of problems like this before. Let's first start with the F is equal to ma. So F is equal to ma, and I'm going to look at this from the perspective of the satellite. So the force that is applied to the satellite by Eros would be a force pointing towards the center, because in order to keep the satellite on a circular path, there has to be this thing called the centripetal force. Right? So this is the force of the satellite, and it is a centripetal force. That will then equal the mass of that particular satellite, because it's the force necessary to keep it in its orbit, and therefore I would be talking about the mass of that satellite, and then multiplied by the acceleration this satellite is experiencing, right? And that would be a centripetal acceleration because it would be pointing towards the center of an orbit. So now that we detailed that, let's talk about this formula. Okay, this says that the force of gravity essentially is equal to the gravitational constant multiplied by the mass of one object by the mass of the other divided by the distance between them squared. So how is the force of gravity and the centripetal force related? Well, they are the same, right? So the force due to gravity between these two objects, okay, from the perspective of the satellite would be a force pointing towards Eros, again, towards the center. So this is really the force, this could be considered the force on the satellite, and it is a centripetal force. Okay, so basically what I can do here is I can substitute this value on in for that. Right, and when we do that, we get something like this, where it says the mass of the satellite times the centripetal acceleration of that satellite should equal the gravitational constant multiplied by the mass of the satellite, which is one of the objects, and the mass of Eros, which is the other, divided by their distance between them squared. Now, notice what happens to the mass of the satellite. Bing, bam, boom, goodbye. So now what we can do is we can write the centripetal acceleration of the satellite is equal to the gravitational constant multiplied by the mass of Eros all over r squared. Now, they want us to know the orbital speed, not the centripetal acceleration, but now you want to start thinking, well, what is the relationship between centripetal acceleration and linear speed? Is there a relationship? And you say, oh my goodness, there is. Look at that formula over there on the right-hand side. So I know that the centripetal acceleration is equal to the linear speed squared divided by the radius. So what we can simply do is we can take this value and plug it on in now. Right? We can plug it on in for the centripetal acceleration. What would that give us now? That would give us v squared over r is equal to g times the mass of Eros all over r squared. And notice what happens to the r's now in terms of the math, right? One of them cancels on both sides. So now I'm left with something that looks like v squared is equal to gravitational constant multiplied by the mass of Eros all over r. Again, to solve for v, what would we have to do now? Mathematically, take the square root of both sides. So just to save a little space, why don't we just do that right off the bat here? I'll erase that. And then what we'll do is we'll put the square root sign here, and voila, there's the equation. So now let's just plug it in. So it's going to be the square root of gravitational constant, which is 6.673 times 10 to the minus 11, multiplied by the mass of Eros, which was 7 times 10 to the 15th. Right? 7 times 10 to the 15th. All over then the radius, which we said was about 150 kilometers. But remember, we have to do this in terms of meters, so just add 3 zeros. And we'll find that the orbital speed, aka orbital velocity, will simply be a square root of 6.673 times 10 to the minus, times 10 to the minus 11, times 7 times 10 to the 15th, divided by 150,000. And what do we get? A very small number, right? This is actually this is very tiny. This is 1.76 meters per second, right? That's a really small orbital speed. That's okay. It's almost a little unrealistic, but it doesn't even matter. This is just in terms of, doing the mechanics of the problem. But if the satellite were placed right, this far away from the asteroid, this would be its velocity. So essentially what we're looking at here is it would not be placed this far away. All right, it would be placed significantly closer. All right, but in any case, the math helps us determine that. So now it says also calculate the acceleration due to gravity, but the acceleration due to gravity, as I spoke about before, should be equal to the centripetal acceleration. So why don't I just use this formula now to calculate the centripetal acceleration? All right, so I'm going to do it over here. So the centripetal acceleration that the satellite is experiencing, which is also the acceleration due to gravity of that particular asteroid, should be the gravitational constant 6.673 times 10 to the minus 11, multiplied then by the mass of Eros, which is 7 times 10 to the 15th. Okay, all divided by then the radius, so 150,000 squared. And you can already get a feel for this. I mean, the way the numbers are going to look, it's going to be really small. I mean, we have a tangential speed of 1.76, right? It's almost comical. But that's just the numbers I use. I chose them randomly. So times then, so 6.673 times 10 to the minus 11th times 7 times 10 to the 15th, all divided by then 150,000 squared. And yeah, look at that. I mean, it's barely even a noticeable force. I think this force is similar to the force of gravity that we experience from the sun. So 2.08 times 10 to the minus 5 meters per second squared. All right. So it can still orbit, obviously, but it's really very much unlikely to, to do so here. All right. But in any case, though, that's how the numbers would work out. So just a made up problem. And guys, thanks so much for tuning in here. We have finished chapter 6. Moving on to chapter 7. Please stay tuned. We got a lot more stuff coming out to you guys. So, and I do appreciate your viewership very much. And it'd be awesome if you can hit that subscribe button. That would be great. It allows us to help more students just like yourself. And yeah, so that does it for me. Look forward to helping you out with chapter 7. Take care.